we have seen about basic routing, what is it all about. Now, we will go to some specific important and specific routing protocols, and the first routing protocol that we will be discussing today is known as distance vector routing or RIP, routing information protocol. So, RIP, I mean this is the this is one of the oldest routing protocol which was actually used on the internet, and it is still used in today in many places, which is based on distance vector. We will see what the distance vector is. Now, the distance vector of node x is the minimum distance from x to every other node in the network. For example, the distance vector of for A in the following graph is 1 2 2 1 1. That means, for B is a distance 1, for C it is a distance 2, for D it is a distance 2, for E and F these are distance 1. So, 1 2 2 1 1 from A, these are the distance vectors. If you recall from the last lecture, what we said was that this routing problem now we are not talking about forwarding, we have done that. So, the routing problem can be reduced to a graph theoretic problem. So, these nodes are the routers, maybe they could be some hosts also, but let us for the our purpose for RIP we will consider these to be routers, and these routers, and we want to, let us say, the simplest thing when we are not talking about delay, congestion, link capacity, etc. So, in the simplest case this is simply a shortest path problem. Okay. For the shortest path, so this distance is over here, as you can see that the distances are just the number of hops. That means, these links are also not weighted. So, we just count the number of links to reach from the source to the destination, and that is given as the distance vector for that particular node. Okay. So, we will use these distance vectors to compute the shortest path. Only thing is that these distance vectors, so we have to run the algorithm. Obviously, we do something like a shortest path, standard shortest path algorithm, and here in this particular case the algorithm that we will be using is a Bellman-Ford algorithm, and this Bellman-Ford algorithm, but we have to run them in a distributed fashion. That means, this Bellman-Ford algorithm is running at each location. So, this is the Bellman-Ford algorithm. Given directed graph with length d j k, that means, this is the distance vector from j to k assigned to each directed link j k. Assume every cycle has positive total length. This of course is trivial if all lengths are positive, and since we are taking the link weights to be 1. So, this will always be valid. If j k is not included, include it with length d j k set equal to infinity. Goal is to determine shortest path from each node to node 1, let us say, which is the destination. So, this is the graph, and what is this infinity? Well, the point is when you are starting the algorithm, you may not know that you are actually connected the length, that means j may not know that he is actually connected to k through multiple hops. So, he will to start with he will just set it equal to infinity. So, this is just putting it in proper format. Let d I h be length of shortest directed path with at most h arcs from node I to destination. d I h is generated by the iteration d I h plus 1 is equal to min j d I j plus d j h, and d I 0 is equal to infinity. So, if you just I mean you can put all of them as infinity, or the direct links you can take note of them, does not matter, in one iteration that will be taken care of. So, what we are doing is that, so what is this capital D telling us? The capital D is telling us that this is the best path I know at the moment from myself to this particular node, okay, that is at this iteration. Now, in another iteration when these distance vectors are interchanged, we may find that my neighbor knows something which is of a better cost, all right. So, I take this I can go to it from my neighbor using dij over all j and then djh. So, if we keep doing this iteration, how many number of times? Well, if there are n nodes, I need to do this iteration. I mean there will be at most n minus 1 arcs. I mean this is the worst case in which all the nodes are connected in a chain. Now, in that case I need to do at most n minus 1 iterations. So, after n minus 1 iterations, I will get to know about a node which is at a distance n minus 1 from me, because what will happen is that each iteration this information will filter through and then reach me. So, I will know, although to start with this node may have thought that that node is not connected at all. So, d I 0 is infinity, but what will happen is that after n minus 1 after n minus 2 iteration, its neighbor would know that he is connected to that with a distance of n minus 2, and then this information will reach this node and he will know that I can go to my neighbor in one hop and then take n minus 2 hops to that. So, I can reach that node in n minus 1 hops. So, since every cycle has positive length, no optimal path contains a cycle, hence has at most n minus 1 arcs, where n is the total number of nodes, thus at most n iterations including the first. At regular intervals, so what we do in this distance vector routing is that at regular intervals router j sends packet to each neighbor giving new estimation for djk, the current distance to destination k. That means, the router j is giving the djk value and not only djk value for all k. So, that is why this is not just one distance value, but a distance vector that is sent to all its neighbors. So, the neighbors tell each other about the distances they know to a particular node k, and then whichever is better, that means if the neighbor if the node j finds that from node L I can go in a shorter distance after considering the length from j to L, which is again 1, then it will sort of say it will update in its table that for destination k next I will go to L, and this is the distance which is currently estimated. So, the current distance to destination k. So, we do some local exchange of information, local exchange of information between say any router and its neighbors, and then the algorithm is of course running globally and in a distributed fashion. Router I updates its table via decentralized Bellman-Ford iteration. So, dik is equal to minimum over I of dij plus djk. That means, whether it is I mean through all possible all the through from all the neighbors, whether I mean which one gives the minimum distance to a particular destination k. Now, so for IP routing, let us just take a look at the global picture once again. So, there is this routing table which have to be created and which have to be kept updated. There may be ICMP redirect messages from other routers that we have seen, which will make changes to this routing table, and there is a daemon which what it does is, because there is this route command and netstat command which are basically for user interaction. So, we are not going into the details of this. What the routing daemon will do is that from time to time this will run and maybe send packets to the neighboring routers, or run some iterations of this Bellman-Ford algorithm and keep the routing table up to date. Okay. So, for from this routing table we get the IP output, there is calculate next hop router, and if it is source routing, of course we get it, otherwise we get it from the routing table, and when a particular a packet arrives, it sees that whether it is for me. If it is yes, of course, it goes up. If it is no, then it calculates the next hop. Now, we just mention about autonomous systems here. Okay. Autonomous systems are not directly used in RIP, it is used in the other algorithm, but here also it is important because this idea is important, and this is very important for scaling the network. We know that this whatever routing protocol etc., we are following, this has to scale to the global level with all these millions of routers who are connected to each other. Now, all these, as I said, that a router may be connecting a network, there is a network at the back of it. So, we are forgetting about that. Now, a number of routers together may form an autonomous system. So, we are introducing another level of hierarchy. Now, an autonomous system is a region of the internet that is administered by a single entity. Okay. So, this is not just a one network, maybe this is a collection of networks, but still somehow there at some level for some facets of it, it is administered by a single entity, and this is called an autonomous system. Example of autonomous regions are, let us say, some service provider, there is a service provider, maybe MCI or some other service provider, its own backbone network, that may be an autonomous system. A regional internet service provider, that may be an autonomous system. Now, of course, this regional internet service provider is giving the services to so many customers, all right, and each of the customer has its own router connecting to this backbone, and each of the customers will have his own network, all right. So, it is a collection of networks that way, but this is one autonomous system. The idea is that we try to run the same kind of same routing protocol inside an autonomous system. There are two questions here. What is one is that what you run, what is the routing protocol you are running inside the autonomous system, and what are the routing protocols that you are running between autonomous systems, because finally your packet may go from a network to a router to the backbone of the same autonomous system, still remaining in the same autonomous system. Then it might have to hop across some autonomous systems and then finally enter into another autonomous system and go all the way down to a particular network and then to the intended host. Okay. So, autonomous system introduces another level of hierarchy. Routing is done differently within an autonomous system, that is the intra-domain routing, and between autonomous systems, inter-domain routing. So, we are right now RIP is suitable for intra-domain routing. So, we are talking about intra-domain routing for the time being. We will look at inter-domain routing later on. So, the characteristics of distance vector routing is that one thing is that it uses periodic updates. Updates to the routing tables are sent at the end of a certain time period. A typical value is 90 seconds. So, that means every 1.5 minutes you send the updates, that means you send your distance vectors to your neighbors. There may be triggered updates. If a metric changes on a link, a router immediately sends out an update without waiting for the end of the update period, because we want the router to, because this is a very high speed thing. So, 1.5 minutes that we sent earlier, that may be very fine when nothing much is happening, but when maybe some link has gone down or some metric this thing has become really congested and some parameter has changed, at that point of time a router may not wait for the lapse of that 1.5 minutes and send immediate updates triggered by some kind of an event. So, there may be triggered updates. And then there may be full routing table update. Most distance vector routing protocols send their neighbors the entire routing table, not only entries which change. Okay. You in some cases, in the case of a triggered update, you may send only that data which has changed, and then from time to time you send the full routing table, which is your distance vector actually. And route invalidation timers. Routing table entries are invalid if they are not refreshed. A typical value is to invalidate an entry if no update is received after 3 to 6 update periods. Okay. What might happen is that instead of a link going down, a router itself may go down, and then that router is not sending any more update to anybody. but after 3 or to 6 update periods its neighbors find that I am not getting any this thing. So, then it will sort of set maybe that link to infinity, that route will no longer, that route or any route through that particular router which has gone dead, they will become invalid, and this will slowly, this information will slowly percolate through the entire network, all right. So, this is this rapid changing or this change is a problem in routing, because this change has to traverse globally, everybody finally has to know, but it takes time. Okay. So, now this we have seen the distance vector routing, and now we will look at the actual protocol which is called RIP or routing information protocol. This is a simple intra-domain protocol, that means it is in the same autonomous system. Straightforward implementation of distance vector routing as that that is the distributed Bellman-Ford algorithm. Each router advertises its distance vector every 30 seconds or whenever its routing table changes to all its neighbors. RIP always uses 1 as link metric. So, all this business about negative cycles is not there. Maximum hop count is 15 with 16 equal to infinity, which means that you cannot, so you see that is a rather low value for infinity, and the reason why you need to keep that hop count, we have discussed one reason earlier, that a packet which has been misdirected may have to be dropped. And secondly, what we are talking about here, this 15, that means that is giving you the length of the maximum number of hops within this autonomous system, within this domain, all right. Of course, when you go out of the domain, so it is not that from the source to the ultimate destination it has to be less than 16, but within the domain there cannot be more than 15 hops. Routes timeout, that is set to 16 after 3 minutes if they are not updated, this also we have discussed. So, a brief history: in the late 1960s distance vector protocols were used in the ARPANET, which you know is the beginning of our this internet era. So, it all came down from that project. Mid 1970s Xerox network system routing protocol is the precursor of RIP in IP, and then there were some other versions also. Okay. Then this was sort of integrated in BSD distribution of Unix. RIP version 1 was formalized using this RFC, this request for comment. You know that this is the standard way of formalizing things in the internet world through RFCs. So, for any topic in this network you can possibly try to find what is the RFC, and that will give you the most authentic source of information about that. So, RIP version 1 was described in RFC 1058, and then RIP version 2, there were some problems with RIP version 1. So, people came with RIP version 2 in 1993, that was RFC 1388. So, it adds subnet masks, we will see what subnet masks are later on. With each route entry allows classless routing. This was a classful routing, the original version, this is what we will talk about now, and then classless routing was also possible, and current function of RIP version 2 is in RFC 2453, which came out in 98. So, RIP version 1, what is the packet format? We have a command, what kinds of commands are possible we will see, which is the version which will be so command can be either request or response, all right. So, you may either request some information from some other router, or you may be giving information in response to some request. So, this command will be either 1 or 2. Then version would be of course be 1 in RIP version 1, and then you have an address family. So, many, because you see you are and this is 2 for IP, request 0 to 0, this is request full routing table. If you put it this way, which means that you are requesting the full routing table, and then you have the address of the destination where you are sending this message, and then these parts are unused. So, this is 20 byte, this is one route entry. Okay. There may be many such route entries up to 24 more routes, each with of 20 bytes. So, this is actually 32 bits of total. So, this is 32 bits means 4 bytes. So, 4 plus 4 8, 12, 16, 20, all right. So, one route RIP message can have up to 25 route entries, and then cost measured in hops, this is also mentioned. RIP version 2 is an extension of RIP version 1. Subnet masks are carried in the route information. Now, what is a subnet mask? Well, I might as well tell you a little bit about subnet mask at this point. The point is, I mentioned earlier that in your full IP address, which is 4 bytes for the time being in IP version 4. So, you have a 4 byte address, all right. So, 4 bytes is 32 bits, out of which the first part would be the network prefix and the last part is the particular host in the network prefix. Now, the question is that which part of it, how many bits is the first prefix which shows the network and how many bits are there to show the host. Okay, this is a question. Now, there were some standards earlier, these are the so called class full days. So, there are different types of addresses and we will go into the details later on when we discuss IP headers in more detail, but they were you see class A, class B, class C, etc. These are the class full. So, where it is mentioned that the first byte roughly the first byte would be the maybe for a class A address, the first byte is the network prefix, the last 3 bytes are for the host, which means you can have a very large network with a very large number of hosts. On the other side of the scale, you have a class C where 3 bytes would be the network prefix and 1 byte would be the so it is a small network or limited to less than 255 hosts. So, it is but a larger number of such networks are possible. Okay. But even then what happened was that originally the network was not envisaged, it was not envisaged that the network world will grow in such a manner. So, only 4 bytes were kept as this address and this address space really became small. Okay. And when you give one particular network, suppose you got only at you are in an organization who has got say 30 machines. So, you will ask for I mean naturally you will network them and then you will want to connect them to the internet. For that you will have to get some IP addresses. Now, if this network is to be specified completely, then it has to be given an unique IP address for the network prefix part. So, at best what you can do is that give it a class C address which is say 3 bytes long. So, that the next that 1 byte is left over for up to 255 machines in your organization, but then you are using only 20 of them. So, a part of the address space is not used. Okay. Now, in order to do that, people wanted more flexibility in saying that okay, how many bytes contain the network prefix and how many bytes contain the number of hosts. Okay, that means host part of the address. So, for that you have to specify that how many bits. So, now we are going from class full routing to classless routing. So, this classless routing you has to carry that information which is carried in this what is called known as the subnet mask. So, this is possible. So, subnet masks are carried in the route information so that we can do classless interdomain routing. Authentication of routing messages, that was there because the routing version 1 was had no security, all right, and if it has no security, what could happen is that a rogue router might send I mean all kinds of arbitrary distance vector messages to its neighbors, etc., I mean creating problem havoc everywhere, all right. So, this was really I mean of course, when the growth things becomes very big, now then you start thinking of all the different possibilities. So, you try to change. So, some authentication was included in RIP version 2, although the authentication is not very foolproof. but that is another story. Route information carries next hop address and exploits IP multicasting. What is multicasting? Right now we have been talking about unicasting, that means there is one source with one message meant for one destination. Sometimes you want a message to be destined to a group of destinations rather than one. You do not want to broadcast it, you do not want to send it to everybody, maybe there is a special interest group. So, you all only want to send to members of this group, that is called multicasting. So, IP multicasting it exploits in some sense. So, extensions of RIP version 2 are carried in unused fields of RIP version 1 messages. So, this is the RIP version 2 packet format. As usual, the command contains 1 or 2, whether it is a request or a response, and then the version which is now 2 for RIP version 2, then the address family, address of destination, and then cost measured in hops. The point is that so the packet format. So, this was the packet format, I think. Now, that was the original this thing. So, what happens over here is this field is used for the subnet mask for IP address, all right. So, you have an IP address over here, you see how it has changed. So, you have an IP address over here and the subnet mask has come here. So, that now you can do classless routing. Next hop IP address identifies a better next hop address on the same subnet than the advertising router if one exists. So, that may come here. So, these are the changes and used to carry information from other routing protocols, for example, autonomous system number, etc. So, that is comes in this part. Okay. Now, a little bit about RIP messages. This is the operation of RIP in routed. So, this routed is actually a command. So, dedicated port for RIP is UDP port 520, all right. So, I do not want to explain all the things here, and that would be a bit this thing. The point is, if you remember, we had come across TCP and UDP earlier. These are the transmission level protocol, which is at a higher layer protocol than this network layer. So, UDP is one such which has got very low overhead. So, we will talk both about UDP and TCP later on, but right now you see that there is a higher layer protocol and they use ports. Ports means for any message transfer between two nodes, say so many different transmissions may be going on from the same node to different processes in different hosts, all right. In order to I mean sort of demultiplex them, unscramble them, that means when a message comes, you want to know that this is for this particular process in this particular machine. This particular machine you can find out from the IP address, this particular process in that machine, that is designated by a port number. This is a number which is which you get from the operating system if you ask for it. So, for RIP there is a particular port which is specified, which is 520. For standard protocols there are standard ports which are assigned. Two types of messages, one is a request message used to ask neighboring nodes for an update, and response message which contains an update. RIP packets are sent using UDP, hence may be lost. Actually UDP is one transmission protocol which is, as I say, that it has low overhead. The other side of the coin is that it is less reliable than its sister, which is TCP, who is more reliable. So, updates may be lost. Updates are done asynchronously after receipt of new distance vector from any neighbor. If arriving distance vector includes a new destination network, routing table is augmented to include this. That means, routing table now increases in size, and that is very important because when you power up you have your routing table may not contain anything. That as you get more and more information from your neighbor, your routing table grows. Every router normally sends update to each neighbor every 30 seconds, we have seen that. If current route from node K to network I has router N as next hop, and if K has not received update from N for 180 seconds, which is 3 minutes, it assumes failure. Alright, that means 6 such update periods, then it assumes failure of N or the network connecting K and N, it does not matter, either way it is the same for K, and marks the route invalid. Invalid routes will be replaced as soon as a valid one is found. Now, how does it initialize? Initialization, send a request packet command equal to 1, address family equal to 0 to 0, that means you are looking for the IP addresses and all interfaces, that means you flood a request at all interfaces. RIP version 1 uses broadcast if possible, RIP version 2 uses multicast address, this if possible. Basically, we will not go into the details of this. The point is that it I mean when it is initializing, it is asking for information from all possible sources. Of course, its sources must come through one of the interfaces. So, it sends out the request through all the interfaces, maybe one by one or maybe some means that we are not going into that. Requesting routing tables from neighboring routers. That means, we are trying to get full routing tables from the neighboring routers, that is the initialization phase. Request received, when routers that receive the above request send their entire routing table, and response received, update the routing table. Naturally, you update the routing table using your distributed Bellman-Ford. And then after some time, when things are more stable, regular routing updates every 30 seconds send all or part of the routing tables to every neighbor in a response message. And then as we discussed, there are triggered update, whenever the metric for a route change, something maybe becomes invalid, send entire routing table. Issue, one is that security issue, sending bogus routing updates to a router. RIP version 1 had no protection. RIP version 2 uses simple authentication scheme. We had mentioned about this authentication earlier. So, what you may have is a few passwords. Unfortunately, these passwords are of course plain text passwords. So, these are plain text passwords. So, it does not give you too much security, but at least it is better than RIP version 1 which had no security whatever. Okay. There are some problems with RIP. RIP takes a long time to stabilize. Even for a small network, it takes several minutes until the routing tables have settled after a change. So, that is one problem with RIP, and RIP has all the problems of distance vector algorithm, for example, count to infinity. We will come to this specific problem later on. RIP uses split horizon, that means with reverse Poisson, as it is usually said, to avoid count to infinity. Once again, we will tell you what it is when we discuss that. So, this is the count to infinity problem. The problem is routers react to good news quickly. The min operator brings down the value in one go. In a subnet with n hops, every router knows about it in n exchanges. However, it reacts slowly to bad news as other neighbors mislead the routers. Gradually, all the routers count their way up to infinity. Okay. So, this is the problem. Look at this. Suppose these are the 3 routers A, B and C with this thing 1. So, C to C can go to A via B and the cost will be 2, alright. And so, A can go to C via B, cost is 2, B can go to C straight away with a cost 1. Now, suppose the link BC gets down, that means BC goes down, alright. Now, if BC goes down, B immediately finds out about it, immediately or after some period that maybe 180 seconds or something. Anyway, B finds out that C has gone down. So, he does not have any way to go to C. So, he may set C to infinity. But look at what A does. A had CB2. Okay. So, it's basically its routing table says that I can go to C with a 2, because A still does not know about this mishap. So, it will have this C2 in its routing table, which may be sent. Now, so C infinity is being sent from here to here, C2 is being sent from here to here. Now, B sees that A can go to C with 2. So, he will now, for going to C, he will now set A as the next hop and keep a cost of 3. A of course will realize that C, I mean it cannot take that B next B, because B is advertising C as infinity. So, it will make it to infinity. Now, we have C infinity here, C3 here, exchange again. Now, this one becomes C4 and this one becomes C infinity. So, this way both of them start counting to infinity. All right. What was the problem? The problem was A was sending C2, that means A was going to C via B, but it was saying to B itself that it was saying that I can go there at a distance 2, without realizing that this might mislead B. So, one heuristic which was said is that if A is really going to C through B, then to B, instead of saying C2, it should say C infinity. All right. So, this is the hack, so to say, which was used. The reason for the count to infinity problem is that each node has only a next hop view. For example, in the first step, A did not realize that its route with cost 2 to C went through node B. How can count to infinity problem be solved? Well, there is one solution. This is a proper solution, but this is not used in RIP. So, always advertise the entire path in an update message. All right. So, then that means you instead of you give the entire path. If the entire path was given, then this would not have happened, but that is not none. So, if routing tables are large, the routing messages require substantial bandwidth. There is an inter-domain routing protocol called BGP, which uses this solution. We will come to BGP later on. So, the split horizon hack is that a router never advertises the cost of a destination to its neighbor n if n is the next hop to that destination. So, A would never advertise C to B. So, or rather it will send it as a in split horizon with poisonous reverse, it advertises a cost of infinity. This does not prevent 3-way, but as I said that this is a hack, this is not a solution, because this takes care of some of the cases, but this may not take care of all the cases. So, this is the details, I mean where it cannot take, I will come to that later on. So, this is this thing. Suppose you have this network A, B, C, D, E with this kind of cost associated with it. Now, consider the router E. So, E distance tables from neighbors, it may get from A, it may get this 0, 7, infinity, infinity 1, that means A to A is 0, A to B is 7, A to C is infinity to start with, and A to D is infinity. So, this way I mean as we have discussed it proceeds. The point is distance table E sends to its neighbors. So, to A it sends A infinity, because it has to go to A itself. To B actually again it goes directly. So, to B also it sends infinity. To C it that means that what it sends to D, you just look at this value, that it tells that its cost to C is infinity, although to B it says that its cost to C is 4, because to B it says that I can go with a distance 4, because it can take this route from E to C, whereas it advertises a cost of infinity to D, because the path that E thinks that it can take with a cost of 4 passes through D. So, to D it says C infinity, rather than C4 which is advertised to A and B. So, this is the split horizon with reverse Poisson. Okay. But look at this case, suppose we have a network network structure like this A, B, C and D. So, these are all routers which is all very fine. So, they are all, let us say, have a cost of 1. So, in order to simplify things, let us say everything, all the links have a cost of 1. So, now when the link between C and D fails, so what we are saying is that this link, suppose it fails, okay, what will happen? What will happen is that C will set its distance to D as infinity. However, A will then use B to go to D and B will use A to go to D, because there is no reverse Poisson between them. What is happening is that previously B knows that it can go to D through C with a distance 2. A knows that it can go from A to D with a distance 2. Now, C is saying D is infinity, but B is saying D is 2. Now, B then sends to A and A sends to B, and mutually they start counting to infinity, not realizing that they were indirectly, both of them were actually going through C, but there is no reverse Poisson between A and B, there is reverse Poisson between B and C, there is reverse Poisson between A and C, but between A and B there is no reverse Poisson. So, they will mutually start counting to infinity, and once again that is sad. After such updates, A and B will then report new path to C for D and C will use the path. Now, A will tell C that I have got a path to D through B, of course, and C will not know. Now, C will also take that. So, for anything from D it will send it to A will send it to B, and things like this will go on without any packet getting anywhere. We thus have the count to infinity problem again. About other limitations of RIP, that means the simple metric of hop count does not permit traffic cause delays to be taken into account in routing. Okay. So, when we are just talking about the hop count, so this is a limited kind of metric. So, basically we are seeing whether we can reach there at all right. But there are all kinds of metrics which may be important, that means some of the links may be very weak or very low capacity, then again some links may be very expensive, somewhere the reliability may be poor. All these metrics which may be important in today's world where the network communication is very important, that you cannot handle in RIP. Okay. So, that is one problem, limitation of RIP. Another limitation is if 16 hops is regarded as infinity, then RIP cannot be used for networks for which there are distances exceeding 15. Okay. So, if there are distances exceeding 15, then RIP cannot be used. So, by today's standard that may be a small value. If infinity is regarded as corresponding to a larger number of hops, then protocol will be very slow to converge upon initialization or topology changes. The point is that if you see a value of 16, or if something has gone up to slowly has gone up to a value of 16, you know that is infinity and you can forget about it. Whereas, if you had put that simply change that infinity from 16 to 16,000, then you would have to count right up to 16,000. So, the thing would be very slow to converge. Okay. So, convergence rate of the to the proper after some topology change or after some crash etc., that becomes an issue in RIP. We will now just look at an example. So, we have seen it. So, we will just to make these things very clear, we will look at an example. Suppose this is the situation which is, and then the initialization phase A sets itself to 0, D sets itself to 0, E sets itself to 0 and so on, and then they solicit router advertisements. All right. Then what will happen is that when they get the distance vector, so the B will so D will respond and B will respond. So, A would know that these two routers B and D are just my neighbors. So, I can put a distance 1 in B and D and the same thing goes for all the routers. So, they get their next step. So, direct neighbors come in after one exchange, all right. So, if there are values over here like 10, 2, 2 as distances etc., these values get transmitted there. So, we get A0, B10, D1 for A. Similarly, for D it gets E2, C2 and A1. So, that is so this way this routing table starts getting filled up, all right. So, then of course, after the second step you get neighbors of neighbors and so on. So, this routing table has now become 0, 10, 3 etc. So, this is going on like this. Then neighbors of neighbors of neighbors. So, those are basically 3 hops away, and slowly these values are converging to the correct values. You see, from A to D you can go to 1, in A to E you can go with a step of 3, A to C is a 3 and A to B is 10 and A to A is 0. So, now we have got it has stabilized, okay. After 3 hops after 3 iterations it has stabilized. So, now this is all very nice. So, this is a stable convergence, that means no value changes any longer. The ones in red were showing the values which change, but now there is no change any longer. So, now there is a good news, which is that there is a new link has come up between B and C with a distance of 1. So, now this message will start getting transmitted through the network like this. Now, as soon as there is a communication between B and C. So, both of them know that they have. So, C has B as a neighbor with a distance 1 and B has C as with a neighbor distance 1. So, this is the direct endpoints will immediately know, and then in the next step the neighbors of B and the neighbors know. So, the neighbor of C, E, will know, the neighbor of C, which is namely D, that will also know that they can reach B very quickly now. Previously, if you remember, they had values like 11 and 13. So, E had to go to B through 13 when it did not know, because it took the route B to D to A to B. So, that is 2 plus 1 plus 10, 13. But now, since it can go to reach C and 2 and C can reach B with distance 1. So, now it has updated the distance to B as 3 and distance to B as 3. So, from 11 and 13 these values have come down in one hop. A of course cannot still does not know. Now, A knows, so it knows that it from going to B it need not take this very high cost path, it can go via C with a distance of 4. So, now neighbors know. So, once again we have a very happy and stable network. The point was that this good news travelled as fast as the number of hops. Okay. So, it just travels, because in one go in the min function will bring down the value to anything. But now, suppose there is a bad news, that means there is a link has crashed, this link has crashed. Okay. So, C so after that what happens? Direct endpoints will know, all right. Direct endpoints will know that I can no longer go to between B and C. So, B cannot. So, B previously all B's is, you look at the previous one, previous to this, that B for example thought that it can go to A through 4, there is should be another entry that it can go through A through C. Similarly, it can go to D through C once again, through E to E through C once again. Now, when the link from B to C fails, all these entries now become invalid, because this link has crashed. So, direct endpoints would know that and some of their entries will vanish. Now, and then in the next step it will now set to A as 10, and when it gets the entire thing, then it will set to something else. It will get help from neighbors. So, if it can go to A to 10, and A says that I can go to C with a distance 3, D with a distance 1 and E with a distance 3, etc. So, it adds 10 to that. So, B gets all these values. Unfortunately, there is a routing loop now due to inconsistent state information. Okay. Because now C knows that in order to go to B, it can take a path of size 5 of cost 5. How? Because there is no way it can reach B through 5. The point is it has been misled by its neighbors, same thing that was happening in counting to infinity. So, they now mutually start counting to infinity for going to B until they reach a value which will force them to go through this link once again, alright. So, this counting to infinity will continue till again you reach the limit and come back to a stability once again. So, this kind of problem, these kinds of limitations and problems which were there in RIP. So, one thing good about RIP was that RIP was RIP is a simple scheme, simple algorithm. So, actually it was conceived in days when networks were smaller, that was one thing, but it as networks grew bigger and bigger, it had problems. One problem was this counting to infinity problem is actually a small problem, but other major problems why RIP could not be used when the network really scaled up for very big networks was this problem of having a low value of infinity, low value of infinity, and making the value larger makes the problem of convergence worse. That was one thing. And secondly, it was really in you are really doing this in one domain, alright, you are really doing this in one domain, whereas in today's world with millions of networks you require a hierarchy of domains, alright. So, as I said that you require these autonomous systems and other hierarchy, etc. So, that was the other limitation, and the other limitation you remember was that we were unable to talk about the quality of the links, alright. Since we were unable to talk about the quality of the links, some of the routes which RIP might set up may be much less than optical, because I mean one thing is very sure, because there is a lot of difference between between the capacity of the links. Okay. You get capacities like 64 kbps on one end of the spectrum, you get capacities like 155 megabits per second maybe in another side of the spectrum. The point is that these two values are several orders of magnitude away from each other, alright. But RIP has no way of taking all this into account. So, this was also important. So, what happened was that people moved from this to another algorithm called link, which is sometimes called link state algorithm, just as RIP is sometimes called distance vector algorithm because it exchanges distance vectors. Similarly, there is an algorithm which exchanges the state of links globally, alright. So, since it exchanges the state of links globally and then do some local processing, and that algorithm is called open shortest path first. So, OSPF. So, this has got some advantages over RIP. We will discuss the OSPF algorithm in the next class. Thank you. Good day. So, today we will talk about IP version 4, that is the Internet Protocol version 4. This Internet Protocol is really the network protocol of the entire stack, and actually is at the heart of data communication. And as it turned out that it became so successful that also other kinds of communication like voice, video, etc., they are also coming over to IP in a big way in many segments. So, today we will talk about the IP version 4, and Just a quick review of the stack, that IP or the so called internet protocol is designed to connect networks that are possibly managed by multiple organizations or people. Okay. The internet that we see today, that is a connection of networks. So, it is a various networks. So, various networks naturally are owned by various different organizations or people, and they are so managed by different people, but they, if they have to communicate, they somehow have to come together and agree to one central protocol, one central network layer protocol, and IP is that protocol. It may have different physical connections. Naturally, if there are different networks having different connections, so it may have different physical connections, and it may be connected via a sequence of arbitrary intermediaries. Arbitrary intermediaries in the sense that when you are communicating from one, say, computer to another computer, these two networks also may not be directly connected, they may go through other intermediate networks. So, there may be a number of hops before your communication reaches its destination. As we have discussed earlier, because this we have discussed in the very beginning about that layered approach, which is used to simplify the application. We just quickly have a look at the layered approach. This is just an example. Let us say we have HTTP, which is the protocol used in the application layer for web. So, this HTTP protocol, this may use a TCP connection, alright. So, TCP, this is another layer, this is called the transport layer. So, we will talk about this later, which communicates with the IP and which then may communicate with Ethernet. But you please note that below the IP there may be a multiplicity of different data link layer protocols, like Ethernet is one, token ring is another. So, they can communicate because of this integrating protocol IP, which is common to both. So, it is a single protocol at network level, ensures packets will get from source to destination while allowing for flexibility. So, we have this so called hourglass design. So, we have this FTP, HTTP, TFTP, etc., all these different application layer protocols at the top. Then we have the transport layer. So, there are two common protocols are TCP and UDP over here, but all of them to integrate to one single network layer protocol, namely IP, and this IP may connect to naturally different networks running different data link layer protocols. Just to look at how the encapsulation goes, once again we had discussed this earlier, maybe in the first or second lecture. So, suppose we have the user data which is being fed to maybe some application. So, there is now that particular application will have its own header.